Let's have a short discussion about the ideal gas law. The ideal gas law is really just a relationship of all the four different gas laws that we've learned about in this unit. We learned in Boyle's law that pressure is inversely related to volume. So if the volume of a gas increases, we would expect its pressure to decrease. Gay-Lussac's law, Avogadro's, and Charles's three laws, these are all direct relationships. So for example, if we were looking at Charles's law, as the volume increases, so does the temperature. But these are concepts that I would hope you already know. The reason I'm making this video is because I want to talk a little bit about where does R come from, what does R mean, and why is it important in this unit. So yes, R is a constant. We know that P equals pressure, V is volume, N is mass in moles, and T is temperature. But R, where is R? It's nowhere to be found in any of the four different gas laws. And that's because R is just a relationship. It shows how all four of the different variables that we test when we study gases are related to each other, specifically at standard temperature and pressure, STP. So, I really like kind of showing this graphic off where we can see that when you set one side of the equation equal to the other and you take N and T and you divide them over to the left side, what you get is R. That relationship between the pressure and volume and the mass and temperature. And if you actually pay close attention to the ideal gas law here, you can actually see all four of the different gas laws make it into eventually what is R. I can see Boyle's law, I can see Gay-Lussac's law, kind of across there. I can see Avogadro's law, kind of across there. And I can also see Charles's law. Where you at, Charles? Right there. Okay. All of these gas laws, sorry, I spaced out for a second. All of these gas laws, if you plug in STP conditions, all right, standard temperature and pressure conditions, which I guess I'll write over here on the right, at STP, pressure equals 1 atmosphere, it would equal, it could equal 101.3 kPa, but for the sake of our class and our unit, we're just going to say 1 atmosphere. Volume equals 22.4 liters. That's really important because what we learned from this is that, 1 mole, this is what Avogadro actually learned, is that 1 mole of any gas is equal to 22.4 liters. And lastly, we have temperature. And temperature has to be measured in Kelvin for our gas laws here. Big kind of clue to that here actually is if we measured in Celsius, at 0 degrees Celsius, we would always get our R value to equal 0. But nonetheless, if you plug in all of STP, you get that R value, which is 0.08206 liters times atmospheres over mole times Kelvin. And that makes sense, right? Because we have liters, which is volume, atmospheres, which is pressure, moles, which is moles, N is moles, but you could also call it mass, arguably. Don't get that confused with grams mass. We're talking about moles of mass, and Kelvin for temperature. This is really important to understand because I think it makes clear not only where R comes from, but when do we actually use the gas law, the individual gas law problem or equations, compared to when do we choose to use the ideal gas law? Stay tuned for the next video to answer that question.